so one of the main applications of magnetic fields to produce particles travelling in circular motion are particle accelerators. So devices where particles are accelerated. Okay, one of the important derivations related to this I'm about to go through. So, we know that the definition of frequency is 1 divided by the time. Okay? We also know that distance equals speed times time, so we also know that time is displacement divided by velocity. Okay? If we flip this the other way around to make it into frequency, frequency equals velocity divided by displacement. Okay? An object's distance, okay, in a circle is the circumference. It travels around the outside of that circle. Distance is 2 pi r. So, if we substitute 2 pi r in for distance here, frequency equals velocity divided by 2 pi r. Okay? Keep hold of that because we're going to use that later. So, looking at the last video that I put out, we derived radius equals mass times velocity divided by b times by q, where b is the magnetic flux density and q is the charge of the particle. Okay? Here, radius is proportional to mass and radius is also proportional to velocity, and we'll see why that's important in a short while. So, what we're going to do is we're going to substitute this, okay, let's substitute this, the other way around, let's substitute this into here. So let's take that equation and place it in place of the r there. So, f equals v over 2 pi r, v is equal, f is equal to v divided by 2 pi times by this in brackets, which we've obtained from here. The v's here cancel. Okay? So because that cancels, it leaves us with 1 on the top, and it leaves us with 2 pi times by m over bq in brackets because the v is cancelled out. Okay? So, if we multiply the bracket out, we end up with 2 pi m over bq, but because it's 1 on the top, that ends up flipping. So f is equal to bq divided by 2 pi m. Now this is important because this shows that frequency and time are independent of the velocity. Okay? If you increase the velocity of the particle, it will still spend the same amount of time going around that circle. Frequency is proportional to field, frequency is also proportional to the charge. So let's have a look at some of the applications that uses particle accelerators. So, in a hospital, there will be a device known as a cyclotron. There may be multiple cyclotrons. Okay? So, these are 2 bits of metal known as Ds, D-E-E-S, D-E-E-S. Okay? And what happens is you've got your particle source in the centre. So, this could be an ion or this could be a tracer. What happens is this has got an alternating potential difference across with a fixed frequency. So what happens is the particle is fired into the D, it's accelerated because there's a magnetic field going either into the plane or out of the plane. And what happens is, because the velocity is increased with the potential difference, the radius gets bigger. And here I will remind you that radius is proportional to velocity. So if you accelerate the particle, the radius is going to increase, speed gets faster and faster, and then it's fired out to its target. Okay, so that's how a cyclotron works, and the relevant equations for that are here and here. Okay, the other thing that you may have come across if you're an A-level chemist is the mass spectrometer. Mass spectrometers are devices for detecting masses of ions or checking abundances of isotopes as well. So what happens is, your sample is vaporised, and then using an electron gun, it is ionised. Your vaporised ions are then passed through an electric field and then it meets something called a velocity selector. Okay? The job of the velocity selector is to make sure that all the ions that leave this are travelling at the same speed. The reason why is because we don't want there to be 2 independent variables. We want the radius to be dependent on mass, not the radius dependent on velocity. Otherwise we will not be able to detect the mass of the particle. Okay, and what happens is the magnetic field is fired into the plane in this circumstance, and then it deflects different amounts dependent on its mass. There's a detector over here, so it comes down in a circle, and based on the size of the radius of deflection, you can detect the mass of the particle. You may be asked how the velocity selector works. How does the device work to make sure that all the ions are travelling at the same speed? The velocity selector is essentially two parallel electric field plates, okay, with a magnetic field going into the board in this, out of the board in this circumstance. So what happens is this. The electric field has field F equals EQ, and the magnetic field is F equals BQV. So if we put the two fields equal to each other, EQ is equal to BQV, therefore E equals BV because the Q's cancel, and then the velocity is the energy divided by the magnetic field. So what we've got here is the following. All of the particles that are travelling at a speed with this desired ratio will make it through. If they're not travelling through with this desired ratio, they will be deflected. So if V is not equal to EB, then it will be deflected. Therefore, you can specify which voltage, sorry I'm being heckled by a Dalek over here, let's just turn that off. Okay, so here, what you've got is all the particles with a specific velocity that's specified. What happens is you will instruct the machine to make sure it's travelling at a certain velocity, they will travel straight on through. And therefore you can assume that the velocity is all the same and it's the mass that's causing the change in radius. Thank you very much.